Hello, my name is Brandon Coventry, and I'm a PhD candidate in biomedical engineering at Purdue University. And the title of my talk is Shortwave Infrared Neural Stimulation Drives Graded Sciatic Nerve Activation Across a Continuum of Wavelengths. Neural stimulation continues to prove itself as a powerful tool for both clinical practice and basic science applications. Clinical practice includes the cochlear implant, the deep brain stimulator for treating Parkinson's disease, as well as emerging technologies such as the vagus nerve stimulator and the spinal cord stimulator. However, the gold standard of electrical stimulation has been limited in its efficacy due to unintended current spread, electrochemical toxicity, and the need for the electrode to be in direct contact with the tissue. For example, a study by Izzo et al. Compares electrical to acoustic stimulation in the cochlea. The acoustic stimulation found up here in the left. This is a CFOS study. And compared to electrical stimulation down here on the right, we find that the electrical stimulation stimulates a large area of the cochlea and compared to acoustic stimulation. This gives rise to unintended auditory percepts in cochlear implant patients. This can also be seen within the sciatic nerve, in that when a sciatic nerve is stimulated, it will recruit the entirety of the nerve, including distal nerve fascicles, at least to some extent. This is also present in the central nervous system, but we'll only be talking about the peripheral nervous system for this talk. Compounding current spread is also the fact that Faradaic charge injection, which is present even in biphasic current pulses, gives rise to the generation of reactive oxygen species, which over time cause cytotoxic effects upon the tissue. So a more targeted stimulation paradigm could improve patient outcomes by limiting the spread of activation, limiting cytotoxic effects, and driving activation without needing to be in direct contact with the tissue. One such modality is infrared neural stimulation, or as I will call it, INS, which is an optical technique developed by Wells et al. Out of Vanderbilt University, and it uses pulsed coherent infrared light to stimulate nerves and neurons. Importantly, this is intrinsic to the cell, meaning that unlike other optical methods, there doesn't need to be any genetic modification of the organism, and no direct tissue contact is necessary. And so it may seem kind of funny that we throw lasers at every problem, but this works out quite nicely in going back to the previous studies I mentioned earlier. In CFOS studies comparing electrical and optical INS stimulation, we see that stimulation by INS is spatially constrained compared to electrical stimulation and is a function only of the penetration depth of the laser as well as the optical aperture, the size of the optical aperture. This is also found within the sciatic nerve, where it was found that we can recruit individual nerve fascicles by stimulating the sciatic nerve, unlike electrical stimulation. Despite the advantages of INS over electrical stimulation, the mechanisms of infrared activation remain elusive and thus limit the development and application of INS. Previous studies have suggested that optical wavelengths for stimulation lie largely within the far to mid-far infrared range, correlating to peaks in the water absorption spectrum, but this hypothesis has been called into question somewhat by studies showing UV activation as well. A second mechanistic question is whether activation scales with choice of wavelength in a photoelectric-like effect, or if it scales with wavelength and intensity of the light source itself. So the objective of this study is to categorize and characterize activation of the sciatic nerve across a range of near-infrared wavelengths. And furthermore, we want to test whether measurements are consistent with water absorption curves as the primary causative mechanism of INS. So moving to our experimental methods, we utilize rat sciatic nerves post-mortem. We extracted the nerve from the biceps femoralis out of 3 rats and had recordings of over 25,000 nerve responses. The nerve was placed within a artificial cerebral spinal fluid bath solution, and we recorded differential compound nerve action potentials, or CNAPs as I call them. We were able to tune the laser between 700 and 900 nanometers with power levels between 0 and 13 milliwatts. And our pulse widths, importantly, were set to 1 nanosecond from the laser itself. This is important because most studies have pulse widths that are comparable to electrical stimulation, so this is a new optical paradigm within INS as well. It is also important to note that for our laser application, our energy deposition is both through acoustic means and thermal means. For our modeling, we were wondering if there is an intrinsic difference in energy deposition throughout the tissue itself, ignoring the active nerve processes. For that, we use MCX Lab Monte Carlo optics simulations, which runs on GPUs. We created a model of the tissue media using the modified Jacques equations to account for wavelength variations and in absorption and scattering. And with that, we measured both fluence rates as well as energy deposition. So looking at our results here, the hypothesis with the model is that if there are differences due to wavelength in nerve activation, this should be reflected within energy absorption within the tissue. Looking at fluence rate, which is photon movement through the cross-sectional area of the tissue, as well as energy per voxel, we find that there is no difference between the spread of activation or the relative energy at any given point between 700 and 800 nanometers. So this sort of violates our initial hypothesis. Quantifying this a bit and looking through the midpoint of our data, we find again that the fluence rate as well as energy are effectively the same within our model. Moving to our physiological experiments, we begin by looking at CNAP activation at a fixed wavelength, starting at 700 nanometers, and varying the pulse energies. And we find that sciatic nerve responses are graded with increased laser intensity driving larger sciatic nerve recruitment, as seen here in these individual CNAPs. Now, this is interesting because it casts some doubt upon a photoelectric-based effect, because this seems to be intensity dependent, where photoelectric-like effect would be agnostic to optical intensity. So moving on and looking at wavelength and optical power level dependencies, like on these evoked responses, we see that there are very distinct activation profiles that arise in different wavelengths at different power levels. In fact, running a two-way ANOVA shows statistical differences between 700 nanometers and every other wavelength tested. Furthermore, when we look at the factor of laser power, we find that every wavelength at every power level is statistically different from each other, with the exception of 750 to 850 nanometers from 0 to 4 milliwatts, and then 800 and 900 nanometers from 8 to 12 nanometers, and 750 and 900 nanometers at 4 to 8 milliwatts. So these unique activation profiles are likely from intrinsic excitation and absorption properties of the nerve and its molecular composition, and not due to just pure energy deposition as predicted within our model. So what could be driving this is still not entirely understood. It could be from specific chromophores, maybe within the mitochondria, which are known to absorb wavelengths around this region and then drive intercellular calcium cycles. Another possibility would be heme group absorption within the nerve, which would show degraded responses as the wavelength is rev shifted away from 700 nanometers. Further studies will be needed to look at this a little bit more closely. So the study demonstrates that INS is not limited to a small subset of optical windows as presented by other studies, and that optical stimuli at different wavelengths with similar radiant energies can evoke different CNAP activation profiles. This means that laser stimuli can be fine-tuned to create these specialized activation profiles for stimulation-based therapeutics. Say that you have a particular penetration depth within tissue that you want to activate at a certain level, well, you can use these activation profiles to guide the choice of optical wavelength and stimulation power to get very, very fine targeted stimuli. If you have any questions regarding this proceedings, feel free to email me at my email address here. And with that, I would like to thank you for tuning into my presentation, and I hope you enjoy the rest of your conference.